So our first speaker today is Shihoko Ishii, who will talk about singularities of pairs and positive characteristic and the characteristics.
Can you hear? Okay. I'm very happy to give a talk at this honorable conference. Okay, my talk is about the singularity of pairs in characteristic P and characteristic 0. And the program of my talk is written like this. If time allows, I'd like to give the definition of liftings. Some people can imagine liftings, but I should use the lifting in a specific way, so it appears in the main result. But I am afraid the shortness of time, so I put the main result earlier than the definition of lifting. Okay, so the most studies section, is it too small? Section 1. Most studies of singularities in characteristic 0 based on resolution, existence of resolution of singularity. And secondly, Bertini's theorem. It is generic smoothness of morphism. And the third one is vanishing theorem. Theorem of cohomology of Kodaira type. These hold for characteristic 0, but these are not available in positive characteristic. Okay, so it causes a problem on the studies of singularity in positive characteristic. So my project is to make a bridge here. Bridge here and transport statement in characteristic characteristic 0, which is proved by making use of these properties. And through this bridge, we transport the same statement in positive characteristic. This is my project. And of course, this is a very crazy idea for some problem. For example, for the problem of resolution of singularity, it doesn't work at all. Yeah, but for my problem, it works. Okay, let me introduce our object. Section 2, our object is a pair. Consisting of X and AE, German A to E. This is a variety of a field. And this is a product of ideal AL with an exponent ER. So we write an abbreviation. E is E1 ER. Here we should note that each EI is a positive real number. Okay, the ideal with a real exponent is not an ideal anymore, but it's just a formal product of ideal. Okay, you may wonder why you think such a pair. I will explain about the idea of pair came up in birational geometry. And I'm not a birational geometer, so my viewpoint may be a little biased. But so if you are expert of birational geometry, please correct me. And my understanding is like this. First, we study the singularity of variety X. This is natural, original way to study the singularity. And then the birational geometer study to think the pair consisting of the variety and the divisor. On X. Is it readable? It's too small. It's okay. Okay. Then it's natural because birational geometers frequently use induction of dimension. If you think of the pair n dimension and n minus one dimension, then it's very convenient because you can prepare the next step. So it's natural to consider the pair consisting of variety and divisor. But this is the same as the pair and consisting of X and defining ideal. Defining ideal of D. This is the same thing. Then it's natural to generalize to X and A. Can you read this? This is behind the, it may be difficult. So maybe X and idea. This is natural generalization. German A is just an idea, not necessarily defining idea of divisor. So it's natural. And if you put the integer exponent, this is also natural because it's still an idea. And how about to think of rational number? It may be acceptable because integer exponent this one with a rational number becomes ideal. So it's rather acceptable. But if you think of X E is a real number, real positive number. There are some gaps. So you may wonder why you think such a kind of things. The reason why it appears is in birational geometry. Real exponent appears in the natural way. For example, in B, C, H, M. This is Bilka, Cassini, Haken, and Makanan. Is it right? And in this paper, they think of the limit of I. EI is a rational number. The limit, then they have maybe this may be different. A, some, how to write, E, epsilon. Epsilon, okay. Epsilon becomes as a limit, this kind of pair appears. So it has a meaning of birational geometry. This is a viewpoint of birational geometry. But for my viewpoint, so in my viewpoint, a little bit different. There is a surprising theorem of Kawashita. Theorem. This is surprising theorem. And because of this theorem, I think it deserves to study. Kawakita's theorem. Yes. Probably almost all people don't know. I will explain, and this is one of the main topics, and I will explain it later. And in order to explain, I should prepare some terminology. So I will give the terminology from now. Okay. Now, in my talk, this pair, arbitrary variety, and this real exponent idea is too general. So we treat a simplified object. So in this talk, our object is the following. A, and this is multi-ideal. Right. As I write before, EI is this one, and I is an ideal of A. Now, our setting is this is smooth. Smooth. And this one is ideal with the exponent real positive number. So our setting is the left-hand side is the simplest setting. And the right-hand side is most general setting. Okay? Under this setting, we discuss. Okay. Now, this is up to oh. 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 Okay, thank you. Thank you very much. Now, we prepare the terminology of invariant, which we are thinking of. Section 3, MLD, and LCT. Let A be a smooth variety. Okay, defined of K is a field of arbitrary characteristics at this moment. And take a point 0. Point not necessarily closed. And we give the definition in basic definition. We say that E is a prime divisor. Divisor over A, not on A, over A with center at 0. So it's quite often appears and it's bulky. So we write over A with the center 0, like this. In this talk, we write like this. Is it acceptable? Instead of writing this, we write just like this. It's okay. So E is a prime divisor over A with the center at 0. What does it mean? This is, there exists a birational morphism. Birational. Phi with a bar normal and E is irreducible divisor on A bar. Okay? So on A bar and over A are different. Okay? Some normal variational modification, E appears an irreducible divisor. And the center at 0, it means the image of the generic point of E is 0. Okay, this is the definition. E is a prime divisor over A with the center at 0. Okay. Oh, it's a bit too. It can be more higher. Is it okay? Yeah. Hmm? Mm-hmm. A bar? Divisor. I assume that A is normal. So yeah, Cartier divisor on the generic point. We look at the generic point. So we don't take care of the point. So the more precisely, we should say the value divisor. So now the definition, second definition, let definition 2, let E be a prime divisor over A with the center 0. So it's a convenient abbreviation. Okay, in this case, we can define VE. VE is discrete variation corresponding to E, because the generic point of E, the local ring of the generic point of E is a discrete variation ring. So it determines the discrete variation VE. Okay, this is denoted by DE. And for an ideal of OA, we define VE as a minimum value of VE F. F is an element of A. Okay, so it's a positive integer. Okay, this is the definition. And also another definition corresponding to E is KE it appears soon. Ke is the coefficient of the divisor Ka bar minus phi star Ka at the component E. It means that this one is written as Ke times irreducible component E plus other term. So this becomes a positive integer. And this also has positive, maybe 0, so non-negative integer. So this is in C. Okay. So this is the second definition. And the third definition is the log discrepancy. Definition 3, log discrepancy. Okay. Let E be a prime divisor over A with the center 0, and E is a multi-ideal with multi-ideal. As I already explained, and for this, we define log discrepancy. A, E, A, E, as follows. Ke plus 1 minus sigma EI V E AI. So we can define this number even if EI is a real number, not necessarily integer or rational number. You can define this number. And this number is a real number. Maybe negative or maybe positive. Okay, this is a log discrepancy. And definition is MLD. This is an abbreviation of minimal log discrepancy at 0 A AE. This is defined as an infimum of the log discrepancy. And E is prime. Maybe you cannot, some people cannot see. Maybe. E is a prime divisor over A with the center at 0. Okay, this is an infimum. Definition of minimal log discrepancy. Okay. Now, this is a invariant, very good invariant to describe the nature of the singularity of the pair. Let me show you some nature of this invariant note. So we denote by n the dimension, codimension of the center closure in A. So if you think of the closed point of A, then this is just a dimension of A. But we a little bit generalized. So this is a codimension of the closure of the focused point in the ambient space. Okay, this is n is a codimension, and we assume that this is greater than 2. We assume always in this talk, because this is equal 0. It's not interesting, and the results are almost trivial. So by this n, we have MLD 0, A, AE. The value of this one is greater than or equal to 0 and less than or equal to n hold, or so either this or MLD 0, A, AE is minus infinity. Okay, either of them happen. 0 bar, closure, Zaleski closure, because 0 is not a necessary closed point. So take a Zaleski closure. Okay, so it means that the log discrepancy, once one log discrepancy becomes minus value, then automatically MLD becomes minus infinity. It's okay. This is one typical nature of MLD. And MLD has a property that bigger MLD implies a beta singularity. Beta singularity means close to the non-singular point. So it means a mild singularity. MLD bigger, then the singularity becomes milder. Okay, this is still the definition. And now we should note that since it's defined by infinity, infimum, so sometimes it coincides with some log discrepancy and sometimes not. So we define E prime divisor over A with the center 0. If, no, first we say that E compute MLD 0, A, AE, we say that E compute MLD. If this is the definition, if either this log discrepancy equals to MLD A, or AE becomes negative. In this case, we say that E prime divisor E computes MLD. In this case, it automatically MLD is non-negative because this value is coincide with this one. This one is a real number, not minus infinity. So this case happens only for MLD is non-negative. And this case is automatically MLD is minus infinity. Okay. So this is a definition that the prime divisor computing MLD. So we put this remaining, and then here I erase. Okay. Now I define the prime divisor computing MLD, but it does not exist always. Okay, we should note that in characteristic 0, then there always exists prime divisor over A with center 0, compute M, maybe it's not MLD. Always exists, but for characteristic K is positive case. Such a existence was not known. No. The reason why the characteristic 0 case, the existence of prime divisor computing MLD is depending on the existence of the resolution. Some appropriate resolution, the computing MLD prime divisor appears. But since there is no resolution of singularity, in this case, it's not known. Okay. Now, still some definition. Sorry, I don't listen. Is it a good question? Sorry, I couldn't listen. So, Okay, I hope I can continue. The definition is AE is log canonical. Log canonical. If every AE log discrepancy is non-negative. This is equivalent to MLD 0 AE is greater than or equal to 0. So log canonical at 0. So this is the definition. Log canonical. So log canonical singularity is a marginally acceptable singularity in bilational geometry. Okay, I leave it. Okay. Let me show you the Kawakita's theorem. Kawakita's result. This is for characteristic 0. This said for fixed E and fixed N is a codimension 0 A. The following set gamma N E defined as the set of log discrepancy. N is log canonical at 0, and E is a prime divisor of A with center at 0. Okay, so think of this set. Please be careful that any multi-ideal satisfying log canonical. So you can move A, ideal A, but this subset, this set is discrete set. Since this is subset of G plus EI, Z. EI is real number. So this set has many accumulation points, but still he proved that this set is discrete. So it's surprising for me. So I think that this pair deserved to study. So, and let me show you some known results about the characteristic zero situation. Wait, the time run out. Okay, for known result on characteristic zero case. The first one is LCT. I should prepare the LCT. The definition of LCT 0, A. This case, A is a single ideal. We were thinking of multi-ideal, but here, thinking of LCT, then we use only the single ideal. This is defined as a supremum of C such that A, C is log canonical. Okay. So this is another invariant, important invariant of LCT. Then by this definition, the characteristic zero case, it's known LCT 0 A is a rational number. This is not difficult. The second one is accumulation point of LCT, the set of LCT A belong to, accumulation point belong to Q. Accumulation point. Any accumulation point of LCT belong to Q. This is highly non-trivial, and this is proved by Bertini and Mustache. Okay, and the third one is proved by many people. This is ACC holds in this set, LCT 0, A. For fixed, maybe you should write for fixed N. So maybe dimension, codimension 0, A is N. This is ACC hold. This is also a very, very important theorem and proved by Dufresne, Ein, and Mustacha for smooth varieties case, A is smooth, and generalized by Haken, McCann, and Shu. So this result highly non-trivial, but these are in characteristic 0. Okay, now let's write this B. This is B, this is C, this is D, and we write the discreteness. It's difficult to write, but I will write. But I'm afraid the time. Okay. Anyway, A is missing, but later I will say about it. The except D, the Kawakita's theorem and the C and D very difficult problem, and the proof very elaborated and based on these 3 properties. Without these 3 properties, we cannot prove. Okay. So it's impossible to prove the positive characteristic case in this problem. You cannot mimic their proof in the positive characteristic case. Our proof is different, so making a use of bridge. Okay, the main result and the application. Main result and application, section 4. Now let's K be a perfect field of positive characteristic. Okay, and given an ideal A1, AR, ideal of polynomial ring X n. Okay. Then for any lifting some people may imagine the lifting, but the definition of my lifting is a little bit strict. anyhow, my lifting, there exists my lifting, a to the 1, a to the r in Cx1, xn. Since there is no ring homomorphism from this polynomial ring to polynomial ring, there is no lifting in the canonical sense, but in the lifting in my sense, there exists a lifting of these ideas of A1, A and A1, AR. Okay. Then the following hold, MLD, the origin of affine space with the coordinate ring here, and A, E is less than or equal to MLD 0. This is an origin of this affine space. A to the E for any E, E1, ER. Okay, and LCT 0 is K N AE is less than or equal to LCT 0 AN C A. So this does not make sense. For A is an single ideal. Okay, this holds in general. Okay, so this is a kind of lemma for the main result, or lemma for corollary. Main results does not use this, but corollary use this. Maybe I will use this one. 0 means origin. Both 0 means origin. I use the same notation, but 0 is the origin of this. This is the origin of this. Sorry. Okay, now the theorem is that K is a field of characteristic P, positive characteristic, and for prime divisor over K N over 0. Okay, and E is as usual on multi-ideal on AN K. Okay, then there exists F tilde prime divisor over A, C, N over 0. 0 is the origin of this. This is the origin of this. Okay. And the AI tilde lifting of A, this is a multi-ideal with the same exponent such that Kf tilde is the n-1 plus Ke and Vf tilde A, each, this consists of AI, so how to say, so by abuse of the notation, we write this, and V, E, A, E. So this is the summation of the coefficient of EI times VE AI. Okay, so by abuse of the notation, I write this. So it plays the role of bridge between characteristic 0 and positive character. Sorry, I think I already over the time. But by this theorem, final application, let me write some final application. Corollary for characteristic 0 and K, let A be a variety of over K. K is a characteristic positive, so it's better to write fast. And K, this is a point, and this is smooth point. With the perfect residue field. I don't assume that A is an affine space, but just 0 is a smooth point with the perfect residue field. Then we obtain that discreteness, Kawakita's theorem. Hold for positive characteristic case. For this case, and the notation B and C and D also hold in this case. And characteristic K is positive. So I'm very sorry to exceed the time. Sorry.
Since we are over time and we have a short break, I think ask your questions privately and then let's reconvene and answer.